ability to get programmed. So that stored program concept that was given by von Neumann was basically driving this. And as against calculators, where we had fixed instructions embedded into hardware, we had the ability to give instructions in the form of software to computers. And that ability to be able to program computers was something that was really making the difference. So we could store software. The real difference between software and hardware became clear at that time. And we were able to store software in main memory, instructions in main memory, and we had more general purpose hardware that we could execute anything on. And that is why, we have so many apps. If we need any new feature, instead of devising new hardware for that, for dedicated matter, we will just be writing software codes now. That's why so many programmers exist, because we are now no more bound to going to factories and building custom hardware for that matter. If we talk about processor evolution, it started with vacuum tubes in 1940s. These are a few of the early computers which were having processors based on vacuum tubes. The Colossus from 1943 and the ENIAC from 1946. Soon there was a shift and electronics was getting boom. We had transistor-based computers in 1950. So for example, this is Stradec at Bell's Lab from 1955. And the evolution obviously didn't stop. It did. And we obviously went towards integrated circuits very soon. In 1960s and 70s was the era when integrated circuits was getting to the market. And this is a snapshot of IBM System 360 from 1964. But at that time, it was mainly focused that maybe we should be developing big computers that can serve as many users with dumb clients as possible. And we were serving them from obviously one place. But slowly the focus was shifting towards microprocessors. And it is said that in 1971, Intel 4004 was primarily the first commercial microprocessor that was made available to the market. And then one more thing that emerged in 1965 was Flint's taxonomy. Although microprocessors were late to arrive, but mainframes and these kind of things were already in the evolution. So the principles of parallelism were already under devising. Imagination always exceeds the realities. So people were conceiving these things. And then there was a proper taxonomy that was developed by Flint's. And I guess to date, Flint's taxonomy has pretty much driven the processor design, the architecture design, in terms of parallelism particularly. So Flint said that, okay, you can look at it from two perspectives, from the data perspective and from the instructions perspective. And you can develop this kind of taxonomy that you can have single or multiple data streams and single or multiple instruction streams. And based on those combinations, you can have a taxonomy that can define parallelism. And starting from 1965 to date, this pretty much is prevalent taxonomy that is driving the processor architecture design. So the first one is called SISD, single instruction, single data. So you have one instruction coming from, so can we use this to point? Yeah, so we have single instruction and single data item coming from the pool of instruction and data, whether it is same memory or different memory, and the processing unit is able to execute it. So for example, if we look at the simplest possible instruction that A is given B plus C, so we will be computing B plus C, how will it be happening at the processor level? So it's a simple instruction given in PyCon. So the instruction will be fast. I'll not be going into architectural nitty-gritties, but instruction will be fast. It will be taken to the processor. The next thing that will happen is, if it allows, am I pressing it wrong or is it really a bit hard? Point, is it, I think it is connected to this docking session. So I should be pointing to it, I suppose. Okay, so instruction will be decoded, the processor will understand it and will see that, okay, I have two things to read. So it will read B and C, two variables from the memory, and then it will be computing or executing it. Q. Okay, so it will be executing it. So the sum will be computed. And then the next step is that it also needs to store the result back into memory. So this is how a normal SISD instruction would execute. This is how every normal Python instruction executes at the architecture. Okay. Okay, now, like, what do we need to execute this kind of instruction, the SISD instruction? Well, apart from the evolution that has taken place, the speed-ups and little architectural differences, it will execute in the same way on Intel 4004 or Intel Core i9. There isn't any real difference in terms of general architectural principles that we will exhibit in these regards. And in terms of software, you need like any like simple Python interpreter that can like execute these instructions. So that is SISD. SISD has like primarily nothing to do with parallelism. So the next thing that we see is SIMD, that is single instruction, multiple data. So single instruction, for single instruction, multiple data, we assume that we have a situation that we have two lists that we want to multiply, the corresponding elements in the list. So we multiply them, for example, using this Pythonic style that for PQ in zip, price, and quantity. And then we say we have an output list ST, and we append the product of these two things in that list, right? So how would this execute on a processor? So if these instructions are written in Python in the way, right? We also say that when we code in Python, you use Pythonic way of coding. So zip, for example, is one thing that is regarded as a Pythonic way of coding. So again, the instructions will be fast. In this case, since we have an array of elements or list of elements, so like we have also like included index, we will be reading one pair of numbers of P and Q at one time. We will be computing their product, and then we will be storing the result of that particular pair on the respective index. Now, the next thing is we will have to iterate. Not so simple, but we will have to iterate over this as well, right? So we will go back, read the next pair of numbers, then we will compute their product, then we will store the result in the memory, then we will iterate again as long as there are elements in the array. Okay, so like so far there is no parallelization at all. Now this is another version that uses NumPy. NumPy, if you know, is a like very popular Python library. So that we import NumPy library here. We like, instead of declaring legacy Python lists, we declare two NumPy arrays, and we say that use this for example, price into quantity, ST is equal to price into quantity. So we say that this is vectorized, single loop-free multiplication that we are doing. And we say that, okay, no matter what is the length of price and quantity, we can just put them into this kind of relationship. It will multiply the entire list all at once and store the result in ST all at once. We have avoided loop. But the thing is, there are multiple numbers. So won't we need to iterate at the level of architecture? That's the primary question that we need to answer. So how will it execute? So instruction is fast, right? And in this case, you read P and Q. P and Q are not read as simple numbers. They are read as vectors, and we will soon unravel what we mean by reading vectors in the processor, right? So it's not just like that we will be repeating. We will be computing this product all at once, and then we will be storing the result all at once. And yes, primarily, in principle, we shouldn't be required to repeat in this case, right? So we will just cover the details of like how this thing will be possible now. So like when we say that we are talking about SIMD, single instruction multiple data, that means we will have single multiplication instruction, that is like multiply x and y, right? And we will have multiple streams of, or say pairs of data that will be given to multiple processing units, theoretically speaking, multiple processing units, and it will be computed simultaneously onto this. And obviously, the next question that would emerge is, this should need multiprocessors because we are saying that we will be doing these computations in parallel. Well, the answer is no. We don't need multiprocessor for this, right? So what do we need? Any guesses? No, not at all. Like, let's first conceive multiprocessors and then go to threads. So then we will need single processor, but it must be a vectorized processor, a processor that supports vectorization, right? And like, well, the next thing would be, well, if we are talking about a vectorized processor or a processor that supports vectorization, it must be a special one. No. It's like virtually every processor that you have is vectorized. It has support for vectorization. So when did vectorization first emerge? It was basically an extension as, like it was named MMX, an extension to a legacy x86 architecture of Intel microprocessors in 1997. And what it did was, it provided large registers to pack multiple data items or multiple arguments at one time. So like at the beginning in 1997, it was just 64 bits. And like it just continues in Pentium 3, we had SSE, streaming SIMD. And then in 2011, in Core i7, we got this AVX, that was Advanced Vector Extension. And the latest one that is commercially available is able to accommodate 512 bits of data simultaneously. So like by saying vectorized, it does not mean that we will be able to do everything in parallel, but the opportunity to do many operations simultaneously increases leaps and bounds using vectorization. And yes, it is happening within a single core. Like Intel came up with this, and obviously AMD following that same x86 architecture had to follow, like, and a year later they also provided this in their x86 processor. Okay. Now SIMD, single instruction, multiple data, that is requiring just vectorization on a single processor, has a speed up of tens to hundreds of times over simple SISD instructions that we just discussed in the background first, right? And yeah, regular Python is not SIMD ready. It cannot leverage automatically. NumPy is one such library that is able to leverage this capability of processors. It is something that you have to manipulate at the level of architecture. It doesn't happen automatically. So NumPy is one prolific library that is doing this. We also say that the operation that we just saw, that was like multiplying two lists without a loop, we call these kind of operations vectorization. So like there are two like very famous features of NumPy. One is called vectorization and another is, for example, broadcasting that you may have heard of, right? So NumPy can leverage it, and since libraries like SciPy and Pandas are built on top of NumPy, so by the dint of that, they might also expose the same kind of potential. They inherently cannot do it, but like using NumPy, they can. Okay, now the next thing is that it? So that means one thing is pretty clear, that NumPy, I guess there is a misconception that NumPy maybe uses parallel hardware. It doesn't really inherently does that. So is that it? And like we will not be able to use GPUs in these scenarios? Well, we can. But like default NumPy cannot do that. You need enhanced library supports for that. For example, there is one library named QPy, which can increase the capacity of NumPy, and it can enable it to execute its instructions in the same single instruction, multiple data streams across multiple GPUs, across multiple processors in the GPU, right? And the same kind of parallelism exists in libraries like PyTorch and TensorFlow. Now, one thing I would say is, in addition to this word SIM, is we can say that this is also a kind of data level parallelism. You might have heard this term in architecture. Like we use these two terms. One is called data level parallelism and another is called instruction level parallelism. So like here we are parallelizing over data. Instruction remains the same. We are parallelizing over data. And even if we are going beyond a single processor, going to multiple processors in a GPU, we are leveraging data level parallelism, keeping the instruction the same. And that happens in PyTorch and TensorFlow too. Okay, now the next one is, so we have covered two: single instruction, single data, and then single instruction, multiple data, the third one is we go to multiple instruction streams. And the first one in that is multiple instructions, single data. Now, multiple instructions, single data is something that we say that we have multiple instructions, multiple different heterogeneous instructions operating over single data or the same data. Simultaneously. Now, this is a pretty hard to conceive architectural paradigm, and there are no real practical applications that have been commercially successful. And if I say that missed is missed, that would be all right. So we are happily missing it. There are some like scenarios that people do portray, but the alternatives are still far more interesting and commercially more capable. So that's why this paradigm never really got realized. And the last one is multiple instructions, multiple data, where we talk about true parallelism instead. So in multiple instructions and multiple data, we say that, okay, we will have multiple heterogeneous instructions. For example, we have multiply instruction and we have square instruction. So like we have multiple instructions, at least two are portrayed here, and we have multiple data for multiple instructions as well. So like maybe one set of data is going to like one set of instructions and another set of data is going to another set of instructions, right? So both things are in multitude. That's when we call it MIMD. Okay. Now, is there a way of parallelizing this scenario in Python? Arguably, multiprocessing is a way. So by multiprocessing, we mean the multiprocessing library available in Python. So like, for example, this is a very simple example where we import multiprocessing library, right? So this is the module that can be used to create child processes. If you have gone through operating system, you may have heard of fork join model. So like you can fork multiple children out of an existing process that will run as children process of the parent process. There can be like different configurations possible for that. So this pretty much follows that same model, that you will be creating more processes or child processes out of an existing Python process, right? And for example, in this case, we say that, okay, let's have a list of numbers and we create multiprocessing.pool as pool using this context manager. So what it will do is, by default, it will create child processes out of the existing Python processes, out of the existing parent process, and the number of processes that it creates by default will be equal to the number of cores available on the given machine. So for example, if you have 4 cores, it will create 4 processes. And the next thing we do here is, we say that pool.map process number and number. So we like take the list of numbers and we, for example, will be assigning one number each to the pool of processes that we have created, and the task that we assign to that is this function process number. So for example, we are saying if the number is even, do something else, and if the number is not even, do something else. That's just to like distinguish between the instructions, that we have 2 separate things running on a given set of data. And so this is one way of achieving true parallelism in Python. So like, for example, if we have 4 cores, the process 1 will be running with number 1 in simple context. Process 2 will be running or executing the number 2 out of the numbers list, and 3 will be going to 3, 4 will be going to 4, and 5 is left. So that means by default, we will be expecting that when the first process gets free, it will be taking up the next number to process that one. Oh yeah, sure, please.
So this last line still looks like SIMD, because the same function being called down.
So like just to like portray a very simple scenario, what I've done here is I've differentiated it here.
So the differentiation happens inside the function.
Yeah, inside the function.
Call still looks like SIMD.
Call is like obviously same, but in principle what we say is we should be able to perform different operations on different data, right? So this is a very simple scenario that I could portray in this case.
Isn't this the case with all of forking that you just mentioned? I mean, the function is going to be the same in form and reduce the
It is like we just like address this thing that the function that we are calling is the same within the function. For example, I just like explicitly highlighted that perform a unique computation for each number. So the instruction that we are going to execute is not the same, right? Now you can say that no, I need a separate function for them as well. That's a separate case. We can make code more complex and like achieve that as well in different ways. No, I'm saying this in theoretical sense, right? I'm not talking about, for example, this is not like even folk in that context, but like just theoretically speaking, right? Okay. So this is one way of achieving parallelism in Python. Now, obviously, the natural question that comes to my mind, to anybody's mind, would be that where would multi-threading fit in? Because multi-threading is something that usually is the first thing thought of when we talk about parallelism. So the problem with multi-threading is that the bad boy JIL, that global interpreter law, prevents parallel execution of multiple threads. So like no matter how many threads you create in your Python program, when it is going to go through the JIL is basically a mutex that implements it as a critical section that whoever wants to access it, the interpreter, it is going to be just one. So the interpreter really becomes the critical section, right? So that means no matter how many threads you create, at one time, Python interpreter will be giving one to the operating system to execute. So that's why I have said that SIM can potentially achieve parallelism, but threading is not going. So multi-threading is there in Python. You can use that, but like no matter how many user threads are you creating, at the system level, Python is handing over just to one thread as a scheduling candidate. So it is not going to leverage parallelism. Then obviously we talk a lot about libraries. That are there any libraries that really make use of this MIMD paradigm? So in fact, as far as I have researched, the libraries mainly live with data level parallelism. So like we talked about, for example, libraries like TensorFlow or PyTorch, which are like leveraging the capacity of GPUs to like carry out multiple executions across multiple processors, but they mainly are doing data level parallelism. To conceive real scenario of instruction level parallelism or multiple instruction, multiple data, it is really hard to conceive. People often talk about like libraries like Dask, but like it is subjective that whether it really achieves that MIMD or not. So in general, what I've figured out is other than using multi-processing, there is no real natural way of achieving multiple instruction, multiple data paradigm in Python. So to conclude, SISD is any regular Python instruction that is like working as SISD, and it would execute on any processor that you have. SIMD, single instruction, multiple data, that is also regarded as data level parallelism. Well, NumPy, and by the dint of NumPy, SciPy, and Pandas also has that capability. And this doesn't require a parallel processor. It can run on any vectorized processor, and any processor that you're using today is vectorized. And like there are libraries like QPy and TensorFlow and PyTorch, which basically can extend this SIMD operation to multiple processors in terms of, for example, GPU. And the third one is SMISD, that is missing so far. And the final one is MIMD. So like multi-processing is a way so that you can use that library to create parallel scenarios in Python. Multi-threading isn't, because JIL doesn't really allow it. So that's it from me. If you have any questions, please. Yeah.
Why doesn't Python support multi-threading? Because I mean, at the base level, for all languages that support multi-threading, at a single instance, a single set of instruction is being executed, and what happens is that the instruction of one function is executed, then the processor is handed over to the other, and then back. So that's how it happens. So why can't that happen in Python? I mean, at a single level, one instruction can attain the
why can't it parallelize in simple terms? So basically, or we can say that why does JIL become a blocker here? Right? Why does it become a critical section? Well, the widely quoted reason is that the way Python was developed, it started in 1991. So it became popular at a very later stage, right? So inherently, the way it is designed, it does obviously automatic memory management. It handles all the memory dynamically. So the problem that it really faces is in terms of memory management, and there are some other aspects too that makes it hard to allow JIL to be avoided or bypassed and allow more than one objects to be accessed at one time by a process. So somehow it makes it memory management and some other aspects vulnerable. And by design, it has it is not something that is desirably so. It is just by design so. And there is a proposal, I guess that is PAP 703 from Meta. There's a talk on that topic tomorrow as well. So that is basically proposing to make JIL optional. So in future versions, you might be able to see, it's still not standardized fully. So you might be able to see JIL being removed and then multi-threading taking advantage. Another thing, C, any language that is implementing threading does not automatically mean that the threading is also making it parallel as such, because one is called user level threading. So any high level language basically is doing user level threading. And then there are system level threadings, which are basically managed by operating system. So for example, if we know about pthreads, which is a very popular library, so they provide the support for both kind of threads to be created. You can create system level threads and user level threads as well. So now the user level thread, will it map to one kernel thread or not? That goes down to operating system again. That is again not something that the language controls itself. So the subjectivity remains anyhow. Any other questions? Yes.
Yeah, something is unclear to me. The other two contenders to the most popular interpreted languages, JavaScript and Ruby, they also have this JIL, right? So they face the same problem with threads, right?
Well, if they have JIL, they should face the same problem with threads.
But that's the thing. I don't know. I don't understand why we always talk about the JIL in Python and not in other languages.
Well, I don't really know the context of those languages.
Me neither. That's why I'm asking.
So I can't say that. I can only say theoretically that if something is really driven by JIL, you can create threads in Python as well. No one is preventing you, and people would be writing multi-threaded programs. I guess there would be people. Anybody has written multiple threads in Python? 1, 2, 3, 4, 5, 6. So obviously no one is, not everyone is programming Python to very serious levels, but anyone who is, there's a very so one more thing that I think is contextually relevant here is that there is not just to say that threading is important merely for parallelism. Sometimes the nature of the tasks are also this way, that something is going to block, something is going to sleep, something is going to wait for an event. So you can create this kind of multitasking. It's saying you have CPU bound jobs and IO bound jobs, which make your processing work better. Threading can help in many different tasks as well. It's not just parallelism. So despite the fact that JIL is there, people haven't stopped using threading in Python. So that means performance is not just the one purpose that it is serving.
I think two questions here specifically, if I may. I don't understand Python at such a deep level, but so when I apply a function to a data frame, right? Suppose it's the same function, right? At the back end, I'm assuming it's just confirming. Is it vectorizing it and then applying it to the data frame, or is it a
okay?
And the second question, sorry, let me just ask both at the same time. The other one is just an example of threading in Python. So especially in web scraping examples, I've experienced this myself, right? So whenever I have a single-threaded web scraping operation, really slow. Whenever I have multiple threads, it's 5 or 6 times faster than doing it in a single thread. So are you saying that the backend is not really creating multiple threads? How is that really?
Okay, so the first question is regarding data frames. So I said that SciPy and Pandas can basically benefit from NumPy. So that means any operation that is happening in Pandas will depend that how it gets translated. For example, that NumPy is not going to accommodate text, right? So that means there will be scenarios where vectorization will be taking place. I cannot exactly lay it out, but there will be scenarios where vectorization will be possible because pandas is not applying that directly.
Suppose if I have a lambda function which is x plus 10, for example. Right? Simple like dividing 10 to each value.
Yeah.
Is that vectorizing?
Well, I cannot say that it is vectorizing, and I cannot also say that it is not vectorizing. So, for example, if you're talking about just Python, no, there is no vectorization at all. Python by default has no vectorization. So for data frames, it depends the way it gets. Does it get translated to a NumPy array? If it does, it is getting vectorized. If it is doing something of its own, right, then it won't be, because both of these libraries are not directly using vectorization. They are using vectorization by the dint of NumPy. And the second question that you said is about threading. I guess if I just be quick about it, if you're going over a network, right, that means you're depending on network as well in some way. So you're requesting to a server, right? So it also depends the way server interacts with you, right? So I cannot exactly explain what goes on at the back end, but within a system, it might be a little more predictable to say that what is happening. When you go to a distributed scenario, it might be a lot more factors playing at the back.
I think that's it. If anyone has any more questions, you can definitely reach out. And
Okay.
we have another
Thank
topic
you.
on the-